In this chapter, we're going to discuss acids and bases. By the time we're done with the chapter, you should be able to complete an acid-base chemical reaction, be able to calculate some pHs, understand acidity, and do some exciting stoichiometry problems involving acid-base chemical reactions. A lot of the vocabulary we use in acid-base chemistry is used in our society. So hopefully the new words that we give you that are presented are words that you're familiar with. And one of the first ones we're going to introduce is acidity. And I'm pretty sure acidity, you've heard that on a commercial. Acidity refers to the concentration of the hydronium ion. The hydronium ion is present in any aqueous solution. If you had pure water, it's present. Acidity and its relationship to the hydronium ion concentration, as hydronium ion concentration increases, acidity increases. Acidity decreases as the hydronium ion concentration decreases. So, in your stomach, which is relatively acidic, there's a high concentration of the hydronium ion. In your cellular fluids or in your blood, where it's less acidic, the hydronium ion concentration is smaller. What's also interesting about aqueous solutions or in pure water, the hydroxide ion is also always present. What's also interesting, as the hydronium ion concentration increases, the hydroxide ion concentration decreases. Or, if the hydroxide ion concentration increases, the hydronium ion concentration would decrease. Acidity is also reflected based upon the hydroxide ion concentration. So, with that concept in mind, you should be able to fill in this blank. As hydroxide ion concentration increases, acidity changes. It either increases or decreases. Pause the video, fill in the blank, unpause the video when you're ready to check your answer. If you have a high hydroxide ion concentration, it means you have a relatively low hydronium ion concentration. Low hydronium ion concentration, that decreases, acidity is decreasing. So it decreases. This means in your stomach, where it's pretty acidic, the hydroxide ion concentration is relatively low. In your blood, where acidity has decreased, the hydroxide concentration would be higher compared to your stomach fluid. Some of you at this point may be asking, how could there be hydroxide ion and hydronium ions in water? Even if it's pure water, how are they created? Well, if it's pure water and they're being created, it must come from the reaction of water molecules. We'll look at this reaction a little bit later, but two water molecules can collide, break some bonds, and form a bond, and form the hydroxide and the hydronium ion. This reaction always occurs. This reaction, this equilibrium, is always trying to be established. So, if you change one of these concentrations, if you increase one, the other one's going to decrease to get an equilibrium ratio for this particular reaction. That's why if the statements down below where we said one increased, the other decreased, it's coming from this equilibrium, this reaction that occurs in any aqueous environment, whether it's pure water or some other mixture. Chemicals that are considered acids and bases, these are chemicals that change the concentration of the hydronium ion and the hydroxide ion. In a few slides, we'll see the specific definitions of acids and bases. But in general, when you add a chemical that's considered an acid, when you add that to an aqueous solution, the concentration of the hydronium ion increases. When you add a chemical that's considered a base, when you add that to an aqueous environment, the concentration of the hydroxide ion increases. And a couple last comments about the hydronium ion and the hydroxide ion. If you remember in laboratory, we've worked with some acid and base solutions, and I've warned you that that 6 molarity HCl solution could break down your structural proteins on your skin. Well, I wasn't exactly telling you the whole truth. It's not the HCl acid molecule that reacts with the protein. it's the hydronium ion that's formed in that aqueous solution that reacts with the protein and breaks it down into amino acids. And it doesn't matter if it's a hydrochloric acid solution, nitric acid solution, acetic acid solution, any acid solution, it's not the acid that collides and reacts, it's the hydronium ion that breaks that structure apart. You'll see this carbon-based chemistry when you take organic chemistry next year. Also in laboratory, I've warned you when we've worked with basic solutions, and that basic solution can break the protein down. What's reacting though, it's the hydroxide ion that's formed in a basic solution that reacts with the protein and can break it down into amino acids. As far as information about the rates of these reactions, well, for the hydronium ion, the more acidic the solution, the higher the concentration of the hydronium ion. The higher the concentration, the higher the rate. So as solutions become more acidic, the rate of this top reaction increases because the hydronium ion concentration increases as acidity increases. For really low acidic solutions, it's a high concentration of hydroxide ion. As the solution becomes less acidic, this reaction increases in rate because the hydroxide ion concentration is increasing. Previously we said that when an acid reacts, a bond breaks, and that bond contains a hydrogen, and that hydrogen comes off without its electrons. And a hydrogen cation was formed. And we sort of implied that that hydrogen cation was all by itself in an aqueous environment. Well, that's not exactly true. That hydrogen cation that forms would quickly, and probably does it during the reaction, forms a bond with another molecule in the solution. And if there's water around, it forms the hydronium ion. The H+, there really aren't any H+ cations in an aqueous environment. The H+ is an abbreviation for the hydronium ion. As stated on the previous page, acidity can be quantitatively described by the concentration of the hydronium ion. However, it's also expressed in a logarithmic expression. This logarithmic expression is called pH. pH equals the negative log of the hydronium ion concentration. This pH equation, like every other equation in this class, is in your information packet. Also remember, this concentration, it has to be molarity. Not percent, not parts per million, but molarity. Shown in this diagram over here, it shows common solutions that you see in your everyday lives and their acidity levels. It also highlights how the hydronium and hydroxide ion concentrations change, meaning as one increases, the other decreases. So in this first column is the hydronium ion concentration, in the second column is the hydroxide ion concentration. When these two concentrations are equal to each other, it's said to be neutral. If you plug this hydronium ion concentration into the pH equation, that pH would equal 7. When the pH equals 7, and for this class, only when it equals exactly 7, will we call a solution neutral. If the pH is less than 7 or greater than 7, if the acidity is greater than 10 to the negative 7th molarity or less than 10 to the negative 7th molarity, it's not neutral. A good example of something that's neutral is pure water. When you have pure water, the hydroxide ion and the hydronium ion concentrations are equal. When the hydroxide and hydronium ion concentrations do not equal each other, the solutions are either acidic or basic. When the hydronium ion concentration is greater than the hydroxide ion concentration, that solution is considered acidic. In our diagram, we see the hydronium ion concentration increasing that way. Under these conditions, those are all acidic solutions. Notice when you plug these hydronium ion concentrations into the pH equation and you get pHs, acidic solutions, the pH is less than 7. Good examples of things that you eat that are acidic: the milk you drink, the coffee that you may drink, vinegar, that may be part of it. Notice pure rainwater isn't pure water. It has carbon dioxide that forms carbonic acid. We've seen that reaction before. It's naturally acidic. Lemon juice, your stomach acid, it's acidic. Its molarity, the hydronium ion molarity, can range during the day because it's a reactant to break down proteins that you may eat, so it can vary. The pH in your stomach acid can range from 1 to 3. But notice acidity increases as the hydronium ion concentration increases. Look what happens to pH. As something becomes more acidic, the pH actually decreases. So what I wrote there, as acidity increases, the hydronium ion concentration increases, and the pH decreases. So something with a pH of 1 is more acidic than something with a pH of 6. Your stomach acid is more acidic than the milk that you're drinking. Also note this scale that we're showing here, it only goes up to 1 molarity hydronium ion concentration. The pH for that calculation, if you did it in your calculator, should give you an answer of 0. Well, we work with acidic solutions that are more concentrated than 1 molarity. The 6 molarity HCl solutions that we've worked with in the laboratory, the molarity of the hydronium ion concentration is greater than 1. And if you plug that into your pH equation, you would get a negative pH. For example, if the hydronium ion concentration was 10 molarity, the pH calculated should be negative 1. The point is, don't be surprised if you get a pH that's a negative value. On this diagram, we're just showing common pHs. The other type of solution, the other name, the basic solution, this occurs when the hydroxide ion concentration is greater than the hydronium ion concentration. When that occurs, it's considered to be a basic solution. When we look at the examples of solutions down here, when that occurs, when you have a basic solution, the pHs are above 7. So your blood, whose pH is around 7.3 to 7.5, it can vary a little bit during the day, that's considered a basic solution. The soap that you use at home, the shampoo, most of those types of products, when mixed with water, form a basic solution. Basic solutions have a lot of hydroxide ion. The concentration is relatively high compared to the hydronium ion concentration. And just as we described acidity above, we can make a comment about how basic the solution is. And if we look at the trend in pH and the trend in hydroxide ion concentration, as the hydroxide ion concentration increases, as the pH increases, the solution is more basic. In the laboratory, we've worked with a lot of basic solutions. A good example are the hydroxide salt solutions that we've worked with. So those dropper bottles that were labeled 6M sodium hydroxide, well, that's really the hydroxide ion concentration. And acidity is related to the hydroxide ion concentration. When it's really high, 6 molarity hydroxide, that's a very basic solution. On our pH scale, we have labeled 1 molarity sodium hydroxide. So 1 molarity hydroxide, you get a pH of 14. If we had a 6 molarity sodium hydroxide solution in our dropper bottle, its pH would be slightly greater than 14. In the laboratory, we have different methods to measure the acidity of the solution, to measure the pH of the solution. The device that's used to quantitatively determine the acidity is called a pH meter. The pH meter is an electrode, and the one we're using in our laboratory looks very similar to this one. There's the electronic part of the instrument, and there's an electrode. That electrode contains a glass membrane that's selective, relatively selective, on what type of chemicals can pass through that membrane to the electrode. And The chemical that can pass through is the hydronium ion. We haven't learned about electrodes yet, but that hydronium ion and that buildup of concentration within the electrode causes a chemical reaction and gives you a voltage. The pH meter, we standardize it, we calibrate it with known solutions with pH standards, and after we standardize it, we can put that electrode into different aqueous solutions and measure pH. It's definitely the most quantitative, well, it's the quantitative way of doing that. We also use chemicals that are called indicators. These indicators are chemicals that have a color, and whether they show a certain color or not depends upon the acidity, depends upon the pH. The first indicator that we're going to use in the laboratory is phenolphthalein. Phenolphthalein, if the pH is less than 7 or less than 8, it's colorless. When the pH goes above 8, it turns pink. So if you put that indicator, some of that chemical into some solution, and it's some colorless solution, and it didn't change color, you know the pH is less than 8. If you put it into a 6 molarity sodium hydroxide dropper bottle, it would turn pink. It doesn't tell you the exact pH, but it tells you the pH in that dropper bottle is greater than 8. So, why do we have a color change based upon acidity? Well, these indicators, they're acids and bases. Shown here is some sort of general chemical reaction for an indicator. So, HIN indicator, acid form, base form, and the hydronium ion concentration is part of the reaction. As this concentration changes, you get a shift to the left or to the right. The indicator, maybe one of them had a color, maybe one of them doesn't. But you get a color change, you get a shift change. So very similar to what we talked about in the previous chapter about shifting and the reestablishment of equilibrium, Le Chatelier's principle. Again, I know that's French, I'm not pronouncing it correctly, but we'll move on from there. If you have just one indicator that's trying to give you some sort of visual idea about acidity, it just tells you whether you're above or below a certain pH. What's usually done to give you a more precise idea of approximately what the pH is to use multiple indicators. Often what is done is multiple indicators are put onto paper. This paper with the indicators is called pH paper. You can take this piece of paper, this strip of paper, put it into some sort of aqueous solution, look at the different colors that are shown from the different indicators, and having multiple indicators will get you a qualitative but more accurate idea of what the pH is. We'll be using these pH papers in the laboratory, and these pH papers will contain 4 indicators. It'll give us a pH that's, plus or minus 1 pH unit. Nothing to the accuracy and the precision of a pH meter, but pretty good to give us a rough estimate of the pH. Okay, let's go ahead and practice what we just learned. Go ahead and do the first practice problem. Pause the video, give it a try, unpause the video when you're ready to check your answer. So, when you calculate the pH, it's always the concentration of the hydronium ion, and it has to be in molarity. Well, we're given that, so that's pretty easy. The molarity is 0.015 molarity. When you plug that into your pH equation, if you figured out how to use your calculator correctly, your answer should be 1.8. And a pH less than 7, that's an acidic solution. Okay, in the next problem, instead of calculating pH, you're given the pH. In your information packet, I've rearranged the pH equation. So right below it is the pH equation rearranged. In this equation, you plug in the pH, and there's a negative there. The pH, the negative pH, is raised to the power of 10, and that gives you the hydronium ion concentration. Use this equation if you're given pH and you need to calculate the hydronium ion concentration. Go ahead and pause the video and answer that question.
Unpause the video when you're ready to check your answer.
So the numerical answer you should get is 4 times 10 to the negative 8th. And just realize, even though we don't see units here, they are there, and it's molarity. So hopefully that answer makes sense. Remember, when you're neutral, the hydronium and the hydroxide ion concentrations are equal, but they definitely equal 10 to the negative 7th molarity. 7.4 is a basic solution. We have a hydronium ion concentration that is less than 10 to the negative 7th molarity. So our answer makes sense. The first definition of acids came from Arrhenius. His simple definition stated that when an acid is put into an aqueous solution, it formed the hydronium ion, meaning the chemical reaction that happened was an acid, like HCl, plus water, forming the hydronium ion. This is a somewhat limited definition, and we'll see a more defined definition in a little bit, but we'll start out with his. Arrhenius also brought up the concept of strong acids and weak acids. So what's the difference between those two? Arrhenius said a strong acid, when it's put into an aqueous environment, completely reacts. So ionizes completely. For our example below, a neutral HCl molecule, if that's put into water, virtually all of them react and form the ion chloride. And that's where the word ionizes completely, how that makes sense. A strong acid, when you put it into water, if you looked at the equilibrium constant, it would say mostly products. Again, there's always an equilibrium. There's always some product and some reactant. But for strong acids, when you put them into water or any aqueous solution, virtually all of them react to form the hydronium ion. If we had a dropper bottle that we've used in the laboratory that was labeled, let's say 6M HCl, HCl is a strong acid. In reality, there aren't any HCl molecules in there. But when we make labels for our chemicals, we label what we're starting with, not really what's exactly in there. This is a strong acid. In reality, it's 6M hydronium ions, because virtually all of the HCl molecules that reacted form the hydronium ions. And this is true for any strong acid. The labeled concentration of a strong acid is really the hydronium ion concentration. And this is something you need to have memorized, and we're going to apply this in upcoming problems. A list, and there's not a big list of strong acids, is given in your information packet. Most acids that we deal with are considered weak, and we'll define weak acids in just a little bit. But we've used hydrochloric acid, nitric acid, sulfuric acid in the laboratory so far, but you'll need to be able to recognize, if given a problem, where to go to see if it's a weak or strong acid. There aren't a lot of strong acids. But if I gave you a concentration and it's one of these strong acids, that's really the hydronium ion concentration. An acid, there's a relatively weak bond in the acid. That bond breaks, that bond contains the hydrogen, and that hydrogen nuclei without the bonding electrons is transferred from one molecule to another. So in this example, the HCl, that bond breaks, that hydrogen atom bonds to the water. That hydrogen atom has no electrons, so it's the hydrogen cation. It's the lone pairs that are on water that form the bond with the hydrogen nuclei that's coming from the HCl molecule. So if we drew the Lewis dot structures, but if we drew it for HCl and water, we can see what's happening during the reaction. For HCl, there's bonding electrons between the H and the Cl. Those bonding electrons are relatively far away from H, really close to chlorine. That makes for a weak bond. You have a collision between these two molecules, and that collision is enough to break the bond. You still need to have some energy to break a bond. But when the HCl and the water get next to each other, that H in the HCl is more has a stronger attraction to the lone pairs on water than it does to its current bonding electrons. And after that collision, this bond breaks, those bonding electrons stay with chlorine and form a lone pair on chloride, and that H forms a bond with the lone pair on water. So there was a transfer of a proton, the hydrogen nuclei, from one chemical to another. There's a transfer of just a positive charge, so H positive. So we form the hydronium ion. It goes from neutral water, gains an H, but it also gains a positive charge. HCl was neutral. It lost an H, it lost a positive charge, so it's negative, and we have chloride. Chloride has one more electron than proton. The hydronium ion has one extra proton compared to how many electrons it has. Okay, weak acids, and the vast majority of acids that exist in the environment are considered weak. And a good example of one that we've used in the laboratory a lot is acetic acid. Acetic acid, it's very soluble in water, and if it collides with a water molecule, so H2O, there's a relatively weak bond in this structure. Actually, there's only one relatively weak bond, and it's this bond that's right there, and we'll discuss why that's the only one that's relatively weak in a second. But that bond can break, and that H can form a bond with a lone pair on water and form the hydronium ion, plus acetate. So, why is the OH bond in acetic acid relatively weak, and why not the CH bond? This OH bond compared to a CH bond, O being a pretty big sun, high electronegative atom, puts those electrons a lot closer to O than to H. But in addition, we have another sun close by, and that pulls the electrons even a little bit further away from that H. Even though this O is not part of that bond, it has a secondary effect. This O here and that H, that's the primary influence on the position, but neighboring oxygens can make that bond even weaker, pull them further away from that hydrogen. A CH bond, their electronegativities are pretty close, and that average position is a lot closer to the middle. By the way, if you didn't have a neighboring oxygen, and if we looked at something like ethanol, which only has one oxygen, yes, that OH bond is relatively weak compared to a CH bond, but the OH bond in ethanol is quite a bit stronger than the OH bond in acetic acid. Having a neighboring big sun, high electronegative atom, can have an influence on bond strength. And for this chapter, acetic acid is considered an acid, ethanol is not. But acetic acid is considered a weak acid. A weak acid means that only a small fraction of those molecules, of those acid molecules that are put into an aqueous solution, actually react. So the vast majority of acetic acid molecules that dissolve, and it's quite soluble, stay as the solvated neutral molecule. Only a fraction react and form acetate. So if we had a weak acid reacting with water, and we saw its equilibrium constant, that K sub C value, but if we looked at it, it should be a number that indicates that it's mostly reactants at equilibrium.
Note that the equilibrium constant, that K value, can be used to indicate acid strength. The K value, remember, is a ratio of product concentrations over reactant concentrations. Here is a K value for a variety of different types of acids. So this is in your information packet. It's given subscript A for acid. So this is the equilibrium constant for an acid reacting with water to form the hydronium ion. So remember, K is products over reactants. So if there's a lot of products, there's a lot of hydronium ions, then the K value will be relatively large. If there's a lot of acid compared to the amount of hydronium ions that are formed, the product, which is hydronium ions, if this was large, then the Ka value would be small. So I'm going to write a statement, and you're going to fill in the word to finish the definition. So here's my additional statement. A strong acid has, and the blank is larger or smaller, equilibrium constant compared to a weak acid. Is a strong acid's Ka value larger or smaller compared to the Ka value for a weak acid? Why don't you go ahead and fill in that blank. So pause the video, fill in that blank, unpause the video when ready to check your answer. A strong acid produces more hydronium ions. It's mostly products. A weak acid, it's mostly reactants. So a strong acid has a larger Ka value compared to a weak acid. So there's problems, study guide practice problems, where you're given the acids, the list of acids. You need to go to your information packet and look at their respective Ka values. The acid with a larger Ka value is a stronger acid.
Arrhenius also gave definitions of strong and weak bases. So again, bases, these are things that make the hydroxide ion concentration increase. Arrhenius's definition of a strong base is some chemical that ionizes completely in an aqueous solution to give the hydroxide ion. So, ionizes completely, forms hydroxide ions, or how about already contains hydroxide ions? Salts, ionic compounds that contain hydroxides, those are bases. And a strong base, for Arrhenius's definition, are salts that contain hydroxide. For example, in the laboratory, when you saw a dropper bottle that was labeled 6M sodium hydroxide, well, if you put sodium hydroxide, solid sodium hydroxide, into water, all of it dissolves to form sodium ions, AQ, and hydroxide ions, AQ. Adding hydroxide ions is making the solution more basic. So that fits Arrhenius's definition. This hydroxide ionizes completely, well, it's already an ion, and forms the hydroxide. One note, though, about just hydroxide salts, it can't be any cation. The strong base definition for Arrhenius, it has to be either group 1 or group 2 cations bonded to hydroxide. So the ionic compound, it needs hydroxide that's part of it. The cations can only be group 1 or group 2. So, to finish my definition, group 1 or group 2 cations bonded to hydroxide are considered strong bases. Okay, another note, if you remember, we said on the previous page, the labeled concentration of a strong acid, that gives you the hydronium ion concentration, and you need to memorize that definition. If you have a labeled concentration of a strong base, like on the dropper bottles that were labeled 6M sodium hydroxide, well, in reality, you don't see any crystals. All those ions become solvated ions, you can't see them. So in reality, that 6M sodium hydroxide, that's really the hydroxide ion concentration. The labeled concentration of a strong base is the hydroxide ion concentration. And it should be easy to recognize. I mean, if you saw this, there's hydroxide in the formula, that's the hydroxide ion concentration. If you saw a labeled acid concentration, there's H's in there, that's the hydronium ion concentration. Okay, Arrhenius' definition for a weak base is very similar to a weak acid. A weak base, it can be quite soluble in water, but only a fraction of them react to form the hydroxide ion. And a good example is ammonia, NH3. In this reaction, the water molecule collides with ammonia, NH3, and the H in the OH bond in water breaks, and that hydrogen nuclei bonds to a lone pair on ammonia. The bonding electrons between the OH and water stay with the oxygen. But ammonia is considered weak because only a small fraction of NH3 molecules that are dissolved chemically react. The Brønsted-Lowry definition of acids and bases came from two different groups independently of each other. One group was the Brønsted group, the other group was the Lowry group. But their definition of an acid, it's the molecule that loses a hydrogen atom and just that nuclei, and it bonds to another molecule. They use the jargon donating proton. A hydrogen cation has no electrons. Its nuclei is just one proton, so it's called a donating proton. But an acid, simply speaking, it's the molecule that loses the hydrogen atom. So, if you were given a chemical reaction and you're asked which chemical on the reactant side is the acid, well, you need to look at the products, what's formed. What's the chemical that loses the H? So, on the reactant side, we have HBr. We have another reactant that contains an H. Which one is the acid? So that's hydrogen carbonate. HBr, if you look on the product side, what forms? Br negative. It lost an H. It lost an H and a positive charge. So it went from being neutral to being negative. HBr, that's our acid. The definition of a Brønsted-Lowry base, that's the chemical in which the hydrogen bonds to. So if we look at this reaction, there's two chemicals. What's happening to them on the product side? So this chemical, there's 5 hydrogens. On the product side, there's 6. It's having a hydrogen cation bond to it. So this neutral molecule on the reactant side has 5 hydrogens. On the product side, it has 6, but it also gained a positive charge, so it's 1 positive. HF lost an H, and it lost a positive charge, so it went to being 1 negative. Note, this base is called methylamine, and next year when you take organic chemistry, you'll be able to name this structure. But the reason why I drew it and named it, this is a base. It has a lone pair that can bond a hydrogen cation. That's a property of being a base. Another concept that should be somewhat obvious, even though I haven't said anything about it yet, acid-base reactions. If you have a chemical reaction in which you have an acid, there must be a base. It's kind of like a redox reaction. If you have something that's being oxidized, you have something that's being reduced. If you have an acid, there must be a base. So up above, HBr was the acid, hydrogen carbonate, this is our base. Something loses a hydrogen cation, something takes a hydrogen cation. You can't have an acid without a base in your chemical reaction. So down below, methylamine was the base. HF in this reaction is behaving as an acid. Acid-base reactions are like any chemical reaction. They're reversible, meaning the products can collide and react and reform reactants. So, if there's an acid-base reaction on the reactant side, the products can react and do an acid-base reaction. So, in this reaction down here, on the product side, one of them is an acid, one of them is a base. Pause the video and label each chemical as either an acid or a base. Unpause the video when you're ready to check your answer. So, reading backwards, so looking at the product molecules, NH4 plus becomes NH3 for the reverse reaction. So it's losing a hydrogen cation and it's bonding to water. Ammonium, NH4 plus, is an acid. Because it's on the product side, it's called the conjugate acid. The water is behaving as a base, and it's called the conjugate base. So in the example problem, we're also supposed to label the acid and the base. On the reactant side, NH3 is behaving as a base, and the hydronium ion is behaving as an acid. You need to look from one side to the other to see what's formed in order to say whether it's an acid or a base. And again, the only difference from one side to the other is a hydrogen and a positive charge. If we look at it, NH3 forms ammonium, the hydronium ion forms water. NH3 is a base, what it forms on the product side is an acid. And chemists say NH4 plus ammonium is the conjugate acid of NH3, the base. Every base has a conjugate acid. What it forms on the product side is an acid. If you have a base, what forms on the product side behaves as an acid in the reverse direction. If you have an acid on the reactant side, what forms on the product side is the base. So every acid has a conjugate base. So NH3 is a base, its conjugate acid is NH4 plus ammonium. We can say the same thing for the hydronium ion. The hydronium ion is an acid, its conjugate base is water. What it forms on the other side is its conjugate. You'll see those as practice problems in your textbook. You'll be given the formula of an acid or base, and you're told it's an acid or a base. And you'll be asked to write the structure of its conjugate. It may tell you that here's a acid, write the conjugate base of this acid. Or here's a base, write the conjugate acid of that base. Some chemicals have acidic properties and basic properties, meaning that chemical has a relatively weak bond that hydrogen's part of, and they have a lone pair or lone pairs that can be used to bond a hydrogen cation. What reaction happens depends upon what chemical is mixed with it, meaning does it behave like an acid or a base? It depends upon the chemical it's reacting with. It's kind of like the Earth. The Earth could lose its satellites to the sun, but it wouldn't lose it to the moon if there was a collision. It depends what it collides with. So in this reaction down here, actually reactions, both of them have hydrogen phosphate as a reactant. In one of them it behaves as an acid, in the other one it behaves as a base. Go ahead and pause the video and label the hydrogen phosphates in both of them as either an acid or a base. Unpause the video when you're ready to check your answer. In the top one, hydrogen phosphate is behaving as an acid, and the bottom one it's behaving as a base. It's not a requirement when you label acids and bases to draw that arrow, but you never know if you need partial credit. Okay, another question you should be able to answer. Okay, if you had hydrogen phosphate, you should be able to write the formula of its conjugate acid, and you should also be able to write the formula of its conjugate base. Go ahead and pause the video and write the two formulas and label them properly. So the answers are in these two equations. We just need to keep it straight. So if you have hydrogen phosphate 2 negative, if it behaves as a base, what forms on the product side is its conjugate acid. So its conjugate acid would be dihydrogen phosphate, H2PO4 1 negative. If you had hydrogen phosphate 2 negative and its conjugate base, it would have one less hydrogen. So it's phosphate. If hydrogen phosphate is behaving as an acid, what forms on the product side is a base. In the next part, we also have amphoteric chemicals. When water is mixed with hydrogen carbonate, two different reactions can happen. In one of them, water could act as an acid, in the other one, water could act as a base. In this problem, you're going to complete the reaction, meaning you're going to write the products. There's two reactants, two products that are formed. The conjugates of both are going to be formed. You're told in the problem whether water is acting as an acid or a base. In the first one, it's acting as a base. In the second one, it's acting as an acid. So go ahead and complete both reactions. Pause the video. Unpause the video when you're ready to check your answer. So, in the first reaction, if water is behaving as a base, the hydrogen carbonate is losing a hydrogen cation. Water gains an H plus a positive charge. Hydrogen carbonate loses an H, so it's CO3, but it also loses a positive charge. So subtract 1 from 1 negative, we get 2 negative. Carbonate. By the way, if you write the formula of a polyatomic ion in one of your reactions that you write in this chapter, and you don't have the exact formula with the exact charge, you probably did something wrong. All of the polyatomic ions that are in this information packet were formed from acid-base chemical reactions. Okay, the next one, water's behaving as an acid, so it loses a hydrogen cation. So it goes from neutral to being negative, and it only has one H, and we form the hydroxide ion. Hydrogen carbonate gets an H and a plus charge, so it forms carbonic acid. Add 1 to 1 negative, you get a neutral compound. One last thing that wasn't asked in the problem, but you should be able to state what happens. If reaction 1, if only it happened, what would happen to pH? Would it increase or decrease? For reaction 2, it should be the opposite. Would pH increase or decrease? Pause the video and fill in those blanks. Get rid of those question marks. Reaction 1 causes the acidity to increase, so the pH, we have to keep that straight, would decrease. When reaction 2 happens, forming hydroxide, that makes it more basic, so the pH would increase. Up until now, we've only presented acids in this chapter with one relatively weak bond. There are many acids that exist that have 2, 3, or more relatively weak bonds. If an acid has 2 or more relatively weak bonds, it's called a polyprotic acid. If an acid has 2 relatively weak bonds, it's said to be a diprotic acid. And a good example of a diprotic acid is H2SO4, sulfuric acid. If there are 3 relatively weak bonds in the acid, then it's called a triprotic acid. And a good example of a triprotic acid is phosphoric acid, H3PO4. Proteins, the reason why proteins have charge, and you'll learn about this in biochemistry, not every protein has a charge, but the ones that do, it's because they have acid-base groups within their structure. Proteins are huge molecules. Some proteins can have hundreds of relatively weak bonds or more. Some less, some more. But it's acid-base reactions that create the charges that are within proteins. All of the polyatomic ions that are listed in our information packet are formed from acid-base reactions. Both sulfuric acid and phosphoric acid are oxyacids. And if we drew the Lewis dot structures, which you've done before, which you should be able to still do, we could see the relatively weak bonds. They're all OH bonds with neighboring oxygens. In sulfuric acid, there's one OH bond that's relatively weak and another OH bond that's relatively weak. For phosphoric acid, there's 1, 2, and 3. Note, sulfuric acid is a strong acid. Phosphoric acid is a weak acid. Does that make sense? We'll look at how many neighboring oxygens sulfuric acid has. 1, 2. Phosphoric acid just has 1. The bonds are relatively stronger in phosphoric acid than sulfuric acid. When polyprotic acids are put into water and a reaction occurs, there's a probability that water could collide with both of those OH bonds at the same time. So 2 water molecules could collide just right at the same time and break both of those OH bonds and form the hydronium ion. But what's more probable is that one collides, and then at some later time, which could be a femtosecond, millisecond, another water molecule collides with the other bond, and it breaks. In general, what's most likely, what's most probable, is that one bond is broken at a time, one hydrogen cation is broken at a time, and removed and forms a hydronium ion, or reacts with some other base besides water. So, when sulfuric acid first reacts, it reacts with just one water. There's a mechanism and we'll have a net reaction, but the first reaction is to react with just one water molecule. So, go ahead and pause the video and complete this reaction with sulfuric acid reacting with one water molecule. Unpause the video when you're ready to check your answer. So, sulfuric acid's behaving as an acid. It loses a hydrogen cation. It goes from neutral to having a charge. Water gains the hydrogen cation and forms the hydronium ion, and what's left is hydrogen sulfate. It's a polyatomic ion that's in your information packet. When you complete an acid-base reaction in this chapter, if you form a polyatomic ion that's not in your information packet, you probably did something wrong. And it's not just the number of atoms, you also have to pay attention to the charge. Okay, this hydrogen sulfate that's produced can then react with a second water molecule, and I want you to complete that reaction. So, complete this reaction showing hydrogen sulfate behaving as an acid. Pause the video and write the two products for this acid-base reaction. When the second collision happens, another OH bond is broken when it collides with water. SO4 1 negative loses a hydrogen and a 1 plus charge, becomes sulfate 2 negative, and we form a second hydronium ion. Usually when we show sulfuric acid reacting with water, we show the net reaction. But there's a mechanism. The hydrogen sulfate, it's an intermediate that's not shown in the net reaction. It's there, but it's not shown. One sulfuric acid molecule is used up, two water molecules are used up, one sulfate is produced, and two hydronium ions are produced, and that would be shown in the net reaction. If you remember our first discussions about acidity in this chapter, we made the statement that there's always the hydronium ion present in water, and there's always the hydroxide present in water. It doesn't matter if it's pure water or if it's a solution, an aqueous solution. The reaction that forms these two ions comes from two water molecules reacting. So as long as you have water, you always have this chemical reaction. You can have other reactions in the water mixture, but you always have this reaction, meaning you always have the hydronium ion and the hydroxide ion. There's an equilibrium constant for this reaction, which means you always have this equilibrium, and if one of these increases, the other one's going to decrease, so that equilibrium ratio is always constant. Acids increase the hydronium ion, which would cause the hydroxide ion to decrease because of this equilibrium ratio. Bases always increase the hydroxide ion concentration, which would cause the hydronium ion concentration to decrease because of this equilibrium ratio. If you have pure water, the concentrations of hydronium and hydroxide, well, if it's just pure water, for every one hydronium ion formed, there's one hydroxide. They're the same concentrations, and at 25 degrees Celsius in pure water, their concentrations equals 10 to the negative 7th molarity. As we learned in the previous chapter, we can write an equilibrium expression for any chemical reaction, and this reaction is no different. We also learned that if there's pure water or pure solid, it's not included in the equilibrium expression.
Since the reactants are liquids, they're not included. The products will be included in the equilibrium expression. And for this reaction, here's the equilibrium expression. It equals the product of the hydronium ion concentration times the hydroxide concentration. This reaction is between water, and because of that, it's given, the K value is given a subscript. It's called the Kw expression. It's the reaction for water molecules. At 25 degrees Celsius, the value of this Kw, the constant, equals 1 times 10 to the negative 14th. So the product of those two concentrations equals 1 times 10 to the negative 14th. And when that occurs, you're at equilibrium. So if you added an acid and increased that concentration, the hydroxide ion concentration would have to decrease so that the product always equals that number. And that's always true. This reaction always happens, this reaction, and an equilibrium is always established in any aqueous mixture. So what are we going to do with this expression? So remember, the concentrations are like variables. If we have this equation down here, this is like x, and that's like y, and it equals that 1 times 10 to the negative 14th. If you know one of the variables, you can solve for the other. The way that we're going to use this equation, if you're given either concentration, you can plug it into this equation and solve for the other concentration. And we'll practice that in problems coming up. This equation, it's also in your information packet, so right below the pH equations, and we'll be using it at least once on your final exam, and many times in your practice problems.
In this example problem on this page, we're in a solution of nitric acid. We're going to calculate the hydroxide, the hydronium ion, and the pH for this solution. We should get a pH that's acidic. We should have a condition where the hydronium ion concentration is greater than the hydroxide ion concentration. But, how do we start this? So, what is nitric acid? Nitric acid, my information packet, it's a strong acid. And remember what we said earlier in the chapter, the labeled concentration of a strong acid, that's really the hydronium ion concentration. And again, the reason is because a strong acid, virtually all of it that you put in reacts and forms the hydronium ion. So even though we have the bottle labeled 0.1 molarity HNO3, it's really 0.1 molarity hydronium ion. The Kw expression, this math function can be used to solve for the hydroxide ion concentration because you already know the hydronium ion concentration. Go ahead and pause the video and solve for the hydroxide ion concentration. When you're ready to check your answer, unpause the video. And plug it in the hydronium ion concentration. The hydroxide ion concentration equals 1 times 10 to the negative 13th molarity. Lastly, you're asked to solve for the pH. So, you have two concentrations. You need to plug 1 into the pH equation. Pause the video and choose wisely. Which concentration are you going to use? Unpause the video when you're ready to check your answer. So, the pH is defined to be the negative log of the hydronium ion concentration, and only the hydronium ion concentration. And it has to be in molarity. So, the log of 0.1 and then change the sign. The pH equals 1. That makes sense. We have nitric acid. It's an acid. We should have an acidic pH. A pH of 1, anything less than 7, any pH less than 7 is acidic. So pH equals 1 makes sense. Always make sure that your answer makes sense. Okay, let's go and look at some problems when we have strong bases. On this page, we're given the concentration of a lithium hydroxide salt solution. The concentration is 0.01 molarity. What did we say earlier? The salt solution, the hydroxide salt solution, what does that mean? If you remember, that's a strong base. It's the hydroxide salt. The hydroxide salt concentration gives you the hydroxide ion concentration. So we already know one of our first answers. And just like our discussion on the previous page for strong acids, the strong base concentration, the lithium hydroxide ion concentration, is the hydroxide ion concentration. And that's true for any group 1, group 2 cation that's bonded to hydroxide. Those are strong bases. And hopefully you can recognize it. The formula of an acid has an H, that's the hydronium ion concentration. Formula of a hydroxide salt, it contains a hydroxide. That's the hydroxide ion concentration when that salt's dissolved in water. Okay, so I want you to pause the video. You have one of the answers. Solve for the hydronium ion concentration and solve for the pH. Unpause the video when you're ready to check your answer. So, since we know the hydroxide ion concentration, we can use the Kw expression to solve for the hydronium ion concentration. And its concentration equals 1 times 10 to the negative 12th molarity. The hydroxide concentration is much greater than the hydronium ion concentration, it must be a basic solution, and when we calculate pH, we better get a basic pH. Hydroxide salts create a basic solution, so make sure that your answer makes sense. Your pH equation again, it's the hydronium ion concentration only. You have two concentrations, make sure you plug in the right one. And when you do, when you plug in the hydronium ion concentration, you get a pH that equals 12. We have a basic solution. So our answers make sense.
In this next section, we're going to discuss the laboratory method that's used to determine the concentration of an unknown solution. This method is called titration. In the laboratory, we're going to look and determine the concentration of acetic acid and vinegar, and we're also going to look at battery acid and determine the concentration of sulfuric acid in that complex mixture. In order to determine concentration, you need to know the amount of solute and divide that by the amount of solution. In the laboratory, when we determine concentration, and for all the lecture and exam questions, the concentration we're going to go after is molarity, which means the amount of solute, that needs to be moles of solute. The amount of solution, it needs to be liters of solution. So if you can experimentally measure both of those, take that ratio, you can get concentration. In any titration method, the first thing that you do is that you quantitatively measure the amount of solution that you're going to analyze through titration methods, which means you accurately measure the volume, the liters of solution that you're going to titrate. In our particular laboratory, we're going to use a pipetter and get 10 milliliters of vinegar, which means you already have the bottom part of the ratio. The next part is to figure out how many moles of solute is in that volume. So our vinegar, we have 10 milliliter solution. Somehow we need to figure out how many moles of acetic acid are in those 10 milliliters. So let me circle what I put. The liters of solution is measured at the beginning, so we know that bottom part. Okay, so how do we determine the moles of solute? It's this part that adds the slight complexity to this problem. This is actually a stoichiometry problem, and you see our B's and our A's listed here. But when you do a titration, there has to be a chemical reaction, and this chemical reaction is specific to your solute of interest. In our vinegar is super complex. There's thousands of solutes in there. You use a chemical reaction that's specific, that only reacts with your solute of interest. Our solute is an acid. For this titration, we use an acid-base neutralization reaction. So somehow we mix acids and bases together, do a neutralization reaction, and we can get the moles of solute. Well, it's a little more complicated than that, and there's a process. Okay, so our unknown, so the moles of solute here, that's our unknown, and we're going to call that our B, like in a stoichiometry problem. You add a solution to that to neutralize your unknown. The solution, though, that you're adding, you have to know the concentration. So the known, the one you're neutralizing your acid or base with, you have to know the concentration. And you add the right amount of liquid so all the acid and base has been neutralized. At that point, under that condition, it said that we've reached the equivalence point. Somehow there has to be some sort of visual clue that you've reached the equivalence point. And what we're going to do is we're going to add an indicator that changes color when you've reached the equivalence point, when all the acid and base has been neutralized. Then, with all that experimental information, you should be able to calculate the moles of solute. Remember, the moles of solute for our concentration, this is our B. This is our unknown. The sample that you know the concentration of, that's your A. The one that you're given information about in any stoichiometry problem is always our A. So, starting with the volume of liquid that you added to reach the equivalence point, starting with that volume, you can eventually get to the moles of your unknown. That volume, that's the volume of your known. You know its concentration. Volume times concentration, that'll tell you how much of the known moles you added to neutralize all the unknown. Our first step in determining concentration from our experimental information, and we're going to determine the moles of A, we're going to start with the known volume that was used to reach the equivalence point. This is step 1. We're starting right there. In the laboratory, you'll be given the concentration of that A, or in a problem, you'd be given the concentration of that A. Concentration times the volume, that'll allow you to calculate the moles of A that were added for the neutralization process. In step 2, you're going to calculate how many moles of solute are in your unknown solution. And again, in a titration reaction, there's a chemical reaction, there's a mole-to-mole relationship. You're going to use that relationship to calculate how many moles of unknown. In the laboratory and in every one of your problems, you would be given the chemical reaction. Once you have the moles of B, then you can plug it into your concentration equation and solve for concentration. So that's the last step. And again, in all the titration ones, you measure out the volume of your unknown and you do your titration, get the data, how much volume was used to get to the neutralization point, the end point. Then you do some stoichiometry, get your B, and you can calculate concentration. Okay, on the next 2 pages, we're going to do a couple example problems. As mentioned on the previous page, in the laboratory, we're going to determine the concentration of acetic acid in a vinegar solution and, separately, sulfuric acid in a battery acid solution. On this page, we're just going to give an example of determining acetic acid, that concentration in a vinegar solution. In the laboratory, we're going to use potassium hydroxide to neutralize all the acetic acid in vinegar. And we'll know its concentration, and it'll be written on the bottles in the laboratory. In this example problem, we'll assume that that's the concentration. It'll be different in the laboratory. Here's our experimental setup. So when we do this, in our beaker, we're going to add 10 milliliters of vinegar. We're also going to add phenolphthalein. That phenolphthalein will be colorless as long as there's any acetic acid molecules in there. When we reach the end point, it's going to turn pink. So how do we add the potassium hydroxide to neutralize the acid that's in the vinegar? Well, we're going to use something called a burette. And this is a burette. It's a volumetric device. It's graduated. It's kind of like a graduated cylinder, except there's a valve that you open and close, and it allows the potassium hydroxide that's in the burette to flow into the vinegar. When you reach the end point, it's going to take less than 1 drop of the potassium hydroxide, and boom, you'll have a color change. So you'll start with the starting volume of potassium hydroxide. As you add, it'll remain colorless. When you reach the end point, when it turns pink, you'll stop, and that difference between the starting and stopping will be the volume of potassium hydroxide that you add. In our example problem, we'll assume that it took 7.5 milliliters of that potassium hydroxide solution to reach the end point. And again, when we started the experiment, we started out with 10 milliliters of vinegar in our container. So, as far as concentration, we know the bottom parts of that ratio. So again, concentration is moles of solute over liters of solution if we're trying to go to molarity. We know the liters of solution. It's 0.01 liters of solution. We're not sure how many moles of acetic acid are in that solution. But we do know from our titration data that we had 0.85 molarity KOH in our burette, and we added exactly 7.5 milliliters, and our solution turned pink. So when we do this titration problem, we have an A and a B. Potassium hydroxide, we know its concentration, that's our A. The acetic acid, it's our unknown, that's our B. So starting with this volume of potassium hydroxide, using its concentration, we can figure out how many moles of KOH were added to reach the equivalence point. Using the chemical reaction, we can figure out how many moles of acetic acid were neutralized. For every 1 mole of potassium hydroxide that was added, it neutralized 1 mole of acetic acid. So concentration times volume will give us the moles of KOH added. The mole to mole ratio will give us how many moles of acetic acid were neutralized. That's how many moles were in the 10 milliliters. Note, this titration stoichiometry outline is in your information packet. We've used this outline before. This one's a little different. We're starting with the volume of A, so we're starting right here. Using its concentration, which is M, using the molarity of A, the known, we can figure out how many moles of A were added in the titration experiment. Using the chemical reaction, we can get to moles of B. And again, that outline in your information packet is the same as this outline. Okay, also remember that molarity, that's a ratio of units, whether it's what we're solving for down here or it's given to you in the problem. So 0.85 molarity KOH means for every 1 liter of KOH solution, there's 0.85 moles of KOH. Okay, so if we start with that volume of A, we need to start with its liter amount. And I'm going to skip that conversion. I'm pretty sure you can go from milliliters to liters now. So 7.5 milliliters is 0.0075 liters. And I'm going to be a little anal with my units. It's liters of KOH solution. And I wasn't anal up here, but I was anal on my conversion factor there. So liters of KOH solution cancels with liters of KOH solution. And that'll tell us at this point how many moles of KOH was needed to neutralize all the acetic acid that was in that 10 milliliters. Okay, the mole to mole relationship for this particular one, it's a 1-to-1. On the next page, when we do an example problem, it's not 1-to-1. But 1 mole of KOH per 1 mole of acetic acid, the mole of KOH needs to be on the bottom. And moles of KOH cancels with moles of KOH, and that equals 0.006375 moles of acetic acid. That's how many moles of acetic acid were neutralized. That's how many moles of acetic acid were in 10 milliliters. So plug that number into here, and that'll give you moles per liter. That'll give you molarity. That'll give you concentration. Plugging in that number, dividing it by the volume, the molarity is 0.638 moles of acetic acid per liter of solution. Note, if you want to write it 0.638 big M acetic acid, that's perfectly fine. Okay, let's go do a practice problem on our own. So here's a helpful example problem for titration. There's 2 parts to it. The first part is actually doing the titration problem, figuring out the molarity of HCl. The second part is figuring out the pH of that HCl solution. Once you go ahead and determine the molarity of HCl, so pause the video, determine that, then we'll go through the answer, and then we'll do the pH problem. So pause the video, unpause the video when you're ready to check your answer. When you have a titration problem that we're working with, there's always 2 volumes in the problem. There's the volume of your A and there's the volume of your B. There's the volume of the known concentration and there's the volume of the unknown concentration. So like any stoichiometry problem, you should label your A and your B. The one that you know something about, that's your known. The one that you know its concentration, that's your known. So the one that's the concentration is given is the calcium hydroxide. That's our A. The one in which we want to figure out the concentration is HCl. So that's our B. Somehow we were able to get some stomach fluid and we were able to get 50 milliliters. We're putting 50 milliliters into our container. The question is, how many moles of HCl are in that 50 milliliters? So we already know the bottom part of our concentration. We know that we have 0.05 liters. How many moles of HCl are in that 50 milliliters? In the titration experiment, it took 12.5 milliliters to reach the end point. The concentration is 0.15 molarity, 0.15 moles of calcium hydroxide per liter of solution. In the reaction, the mole to mole, unlike the previous one in which it was 1:1, it's not. And you know on the exam it's not going to be 1:1. For every 1 mole of calcium hydroxide added, it neutralized 2 HCl molecules. So starting with our A volume, starting with the amount of volume that was needed to reach the equivalence point, starting with the 12.5 milliliters, and I'm starting out in liters because our proportion is in liters. At that point, that'll tell us how many moles of calcium hydroxide were added to neutralize all the HCl. And again, for every 1 mole of calcium hydroxide, there were 2 moles of HCl that were neutralized. Liters of calcium hydroxide cancels with liters. Moles of calcium hydroxide cancels with moles of calcium hydroxide. And we can get the moles of HCl. And that equals 0.00375 moles of HCl. We can then take that number and plug it into our concentration proportion, divide that out, and that'll give us molarity. 0.00375 divided by 0.05, that equals 0.0750 moles of HCl per liter of solution. Okay, lastly, determine the pH of the stomach fluid. Go ahead and pause the video and give it a try. Hopefully you get a pH that says it's acidic. Unpause the video when you're ready to check your answer. So what do we know about HCl? It's a strong acid, and the concentration of the strong acid is really the hydronium ion concentration. Remember, a hydroxide salt, that gives you the hydroxide ion concentration. A strong acid concentration gives you the hydronium ion concentration. So, plugging that into our pH equation, the pH is approximately 1.12. Very acidic. That answer should make sense. In this last part of the chapter, we're going to discuss buffers. Buffers are chemicals that are added to aqueous solutions. The function of a buffer is to minimize the pH changes when an acid or base is added to a buffer solution. So how does this occur? Well, the buffers have at least 2 components. One of them is an acid and one of them is a base. So if you add base to a buffer solution, it's going to be neutralized by the acid. If you add an acid to a buffer solution, it's going to be neutralized by the base. When you make a buffer solution, you choose a weak acid and its conjugate base. So in our example down here, we have acetic acid and sodium acetate. Acetate is the conjugate base of acetic acid. Don't worry about the sodium, it's just a spectator. Acetic acid, if we wrote its structure, the formula for acetic acid is C2H4O2. Acetate, the conjugate that forms on the product side when acetic acid reacts, has 1 less hydrogen, 3, and 2 oxygens. If this is our buffered solution, acetic acid is our acid. If you add any base, it gets neutralized by acetic acid. If you add any acid to this buffer solution, it gets neutralized by acetate, which is our base. In the next slides, we're going to use abbreviations for the acid component of a buffer and the base component. For the acid component, we're going to use HA as the abbreviation for that component and A negative for the base component. So down below, acetic acid, that's our HA. Acetate is our A negative. Also, I didn't completely read this statement fully. It says buffers contain at least 2 components. This example contains 2 components. Your blood, your cellular fluids, contain quite a few different buffering components. Your blood and your cellular fluids, they need to stay at a pH around 7.4. If your pH of your blood was 7.8 or 6.8 for too long, and too long is about 8 hours, you'd end up dying. You'll learn why when you take biochemistry, but for right now, just understand there's many buffering components in there. Carbonic acid and dihydrogen phosphate are a couple examples of acid buffer components that are part of your body. You should be able to write the conjugate bases for both of those. Why don't you go ahead and pause the video and write the conjugate bases for both of those acids. Unpause the video when you're ready to check your answer. So, if an acid reacts, take away one hydrogen and subtract one from its charge. So, what's left is HCO3. Its charge as a molecule is neutral, so subtract one from it, one negative. So, hydrogen carbonate, you'd find that as a polyatomic ion in your information packet. That's the base component of carbonic acid. For dihydrogen phosphate, take away one H, so HPO4, subtract 1 from its charge, so 2 negative. So hydrogen phosphate is the base component of this acid, dihydrogen phosphate. And always make sure your answers make sense. You would find that polyatomic ion in your information packet. You wouldn't find HPO4 1 negative in your information packet. So remember, the charge, getting it right, is just as important as getting the formula correct. There's another concept about buffers that we haven't talked about yet, and that's buffering capacity. If you made a buffer in a beaker, if you kept adding acid, eventually all the base component would be used up. Whatever starting concentration you start out with, that gives you an idea of the buffering capacity. In your body, if you kept eating more and more oranges, putting a lot of acid in there, well, the base components would get neutralized, but your body's not a stagnant beaker. You have organs, your lungs and your kidneys, that help regulate the concentration of your buffering components. You'll talk about that, or you've already talked about that in your anatomy and physiology classes. We'll talk a little bit more using an equation on the last couple slides that gives you an idea of what your body needs to do to maintain a constant pH. As stated on the previous page, when you add an acid to a buffered solution, it's neutralized by the base component. And that may imply that the pH, that the acidity, doesn't change when you add an acid to a buffered solution. It still does. Anytime you add an acid to any solution, buffered or not, the pH is going to decrease. It's going to become more acidic. So what exactly does a buffer solution do when you add an acid to it? It minimizes the pH change, the acidity change, compared to an unbuffered solution. And to understand that, let's give an example of adding an acid to an unbuffered solution and to a buffered solution. And let's just assume we're adding HCl to pure water, so that's our unbuffered solution. Let's say we add HCl, a strong acid, to water, and we form the hydronium ion. If we put in, let's just say, 1,000 HCl molecules, how many hydronium ions would form? So I wrote that as a statement, and I want you to fill in the blank. If we put in 1,000 HCl molecules, how many hydronium ions would form? And once you answer that, why don't you go ahead and say what happens to the hydronium ion concentration, the pH, and the acidity. They either increase or decrease or remain constant. So go ahead and pause the video, answer those 4 things, unpause the video when you're ready to check your answer. So for any strong acid in water, we assume that all of them react and form the hydronium ion. So 1,000. If you're producing more hydronium ions, its concentration would increase. If the hydronium ion concentration increases, it means it's more acidic, and pH decreases. Okay, so what would happen if you added 1,000 HCl molecules into a buffered solution? So here in our beaker, here's our buffer solution. There's our HA, acetic acid. There's our acetate, A negative. If we put 1,000 HCl molecules into there, all those HCl molecules would be neutralized by the base component. So 1,000 HCl's, they would react with acetate, and we would form 1,000 acetic acid molecules. Oh, that's great. We went from this acid to that acid. However, HCl is a strong acid. Acetic acid is weak. It can react, and it can form the hydronium ion when it reacts with water, but it's a weak acid, which means it's not 100%, meaning the 1,000 acetic acid molecules that form, you're not going to form 1,000 hydronium ions. So these acetic acids, we can show it reacting with water in another reaction. So the acetic acid that forms can react with water to form hydronium ions and acetate. But for acetic acid, and we haven't discussed this yet, but only about 1% react. And that's actually something I want you to have memorized. Only 1% of the acetic acids that are put into water or are formed in water react to form the hydronium ion. So, if 1,000 acetic acid molecules are formed, how many hydronium ions would be formed? It's 1% of 1,000, so that would be 10. You're still forming hydronium ions in a buffered solution. The pH still decreases, acidity still increases, but 10 compared to 1,000 in an unbuffered solution, the pH change for the same amount of acid, the pH change in a buffered solution is quite a bit less. It's 1% compared to an unbuffered solution. So a question on your final exam, and there's practice problems like this. If we added a strong acid to pure water, the number of acid molecules put in, that's how many hydronium ions would form. And again, the label concentration of a strong acid is really the hydronium ion concentration. However, if you put that strong acid into an acetate acetic acid buffer solution, and that's the only one I would ask, only 1% of the acid molecules that are put in form the hydronium ion. So a question could be, just like this one, if I put in this many HCl molecules in a buffered solution, an acetic acid buffered solution, how many hydronium ions would form? It's 1%. When you add a base to a buffered solution or an unbuffered solution, the pH always increases. But for a buffered solution, it's not as dramatic. So when you add a base, you always increase the pH. The hydronium ion concentration decreases. The hydroxide ion concentration would increase. The acidity would decrease. It's becoming more basic. But adding a base to a buffered solution compared to an unbuffered solution, you have a much bigger acidity change, pH change, to an unbuffered solution. Shown on this page is an equation that's called the Henderson-Hasselbalch equation. It's an equation that allows you to calculate pH for a buffering solution. Here's pH that you could calculate. This pKa, this is a constant for your acid, and we'll explain that in just a second. So this is a value, and you add it to the log of the ratio of the concentrations of your acid component and your base component. Before we use it, let's explain this constant. So pKa. Well, we've talked about Kas. Remember, that's an equilibrium constant. So here's a page in your information packet. We have a listing of acids and their Ka values. So that Ka value, that's the equilibrium constant for the acid reacting with water to form the hydronium ion. The larger the Ka value, the stronger the acid. And here's a strong acid to help you memorize the concept. So there's HCl, there's its Ka value, mostly products. Remember, the hydronium ion, that's a product for this Ka reaction. So Ka is a constant, and pKa is determined from the Ka value of an acid. pKa looks very similar to pH, but it's the negative log of the Ka value. And if you plugged in the Ka values from that table, you would get values that range from about 1 to 14. The larger the Ka value, the stronger the acid, the smaller the pKa value. So I wrote those statements I just made verbally into statements. Stronger acids have smaller pKa values. And again, the pKa, it's a constant for an acid. Most pKa values, if you plugged them into that equation, would range between 1 and 14. If you had a problem with this equation, which you will on the next page, you'll be given the pKa value. You don't have to calculate it. And we'll see an example of that on the next page. Some of you are actually going to work in the laboratory and make buffered solutions. So how would you do it? By analyzing this particular equation. you can make a buffered solution at any pH you want. But the first thing you need to do is look at an acid and pick an acid whose pKa value is close to the pH that you want to buffer at. So that's the first thing you do. To fine-tune the pH you want to get to, you just change the ratio of those two concentrations. If you had a certain pKa value and you wanted a pH that was lower than that, we'll have relatively more of the acid. If you wanted a pH higher than the pKa value, we'll have relatively more of the base. Base raises the pH, acids lower the pH. This equation can also be used to analyze your body's buffering system. So remember what I said earlier, the pH of your cellular fluids in your blood needs to remain relatively constant. The type of buffering components in you and everybody else is the same, meaning the constants, those pKa values, they're constant in your body. The strategy to keep pH constant is to try and keep this ratio of concentrations constant, meaning the ratio of the acid components and the base components needs to remain constant. It can vary a little bit when you eat foods, but you have different organs in your body that try and keep that ratio constant. And we can use the carbonic acid hydrogen carbonate equilibrium, that buffering system, as an example. Carbonic acid, that's an acid component of your buffering system. Hydrogen carbonate is a base component. Let's say you ate an orange with a lot of ascorbic acid. That acid, when it reaches your blood, is going to get neutralized by the hydrogen carbonate, that base component, which means that concentration is decreasing. To keep this ratio constant, the acid concentration needs to decrease. The carbonic acid concentration needs to decrease. How would your body do it? Well, it uses your lungs. And your lungs, and one of their functions is to get rid of carbon dioxide, and the other function is to bring in oxygen. Carbon dioxide can react with water, and we showed this reaction earlier this quarter, but it can react with water and form carbonic acid. The CO2, that's the waste product of your cells, can react with water and form carbonic acid. If you want to decrease the carbonic acid concentration, will decrease the carbon dioxide concentration. If you want to decrease the HA, the carbonic acid, your lungs should get rid of more carbon dioxide. When you take biochemistry a little bit later, you'll understand this mechanism better and understand how that enzyme, that catalyst, works and functions. But for this class, we're just going to use this equation, the Henderson-Hasselbalch equation, and on the next page, we're going to do a practice problem using that equation. So here's an example problem, practice problem. You have a buffering system and you need to calculate the pH. Like I said earlier, you're given the pKa value. There's the constant for that acid. You're told the concentrations of the buffering components. So one is A negative concentration, one is HA. Remember, the acid component has one more H compared to the base component. The sodiums there are just spectator ions. When you do plug in these numbers and solve, the log there, you need to get the ratio first, that numerical value, and then log it. Just like you log your hydronium ion concentration for the pH. Once you go ahead and pause the video, plug in the numbers, and calculate the pH. Unpause the video when you're ready to check your answer. So, pKa, the 7.21, that's a constant. Plugging in those numbers, we get that ratio. Log 1.6, and you get 0.2041. Add that to 7.21, and you get your pH, 7.4. This, as we mentioned earlier, these buffering components, these are our buffering components that are part of your cellular fluids and your blood. And that's about where your pH is on average throughout the day. This is a typical ratio for those buffering components, for these particular buffering components in your blood and in your cellular fluids. And you don't really need to know this for the class, but there's the approximate concentrations throughout the day. And buffering capacity, how much lemon can you eat, how much Tums can you eat, is related to that. Although again, you're not a beaker, you have your lungs and kidneys that can compensate for eating way too many oranges or eating way too many Tums.